Welcome, everyone. I'm the only one standing between you and the lunch, so I will try to be very interesting and astonishingly fast. In the next 45 minutes, I want to challenge one very common assumption, and the assumption is, OK, you cannot do AI without using frontier, very big, and proprietary models. I'm here to challenge this assumption and to show you that there are plenty of use cases and solutions that can be used to leverage that. Then, first of all, who is the person standing here? I am Italian. As you can probably guess from my accent, I am Chief Technology Officer at Mesa and at Lydia and Overnet. I'm not doing 3 jobs in one. It's just one job, but we are part of a group. And within Overnet and Lydia, we work a lot on AI. Especially with Lydia, we had the very super cool opportunity to challenge the beforehand assumption and to understand how to move from big, expensive proprietary models to something more open. And this is the story that I'm telling you today. By the way, I'm also AWS Hero, Cursor Ambassador, and GenAI Italy and OpenCloud Milano meetup organizer, which means that I'm not adverse to public cloud or to sovereign or to US-based cloud. But in very narrow and interesting and useful cases, we need to make better decisions. Then the assumption is that in 2026, enterprise AI architecture is something different from what has used to be in the past. It is no more about the number of parameters. It is not no more about the huge size of the model. It is a specialized open-weight model running at the edge hardware. And we will see that being able to run at the edge will solve a lot of issues that are difficult to solve on external cloud-based proprietary models. Then, what we are talking about today, just why it is so important now and why it is feasible now. Because we are in the middle of a market shift. And then the small language model ecosystem and how we can address that, how we can leverage that. A technical architecture which worked for us and which could be elevated to a blueprint for everyone wanting to approach this kind of solutions. Then a few words about sovereignty and regulation, because this August, something is going to change. And we have to account about that. And industry evidences, because theory without something working, something put in production is just dumb theory. And action points that you can take your own and start thinking about, start reasoning about how to improve that. Then, about market shift. We are coming out from the scaling race, the so-called scaling race period, which had been from 2023 to 2024-5. And it was just can be stated as larger models, massive cloud clusters, a lot of computing power on the table, no optimization, just bring me your bigger model. And the new release will be bigger than the old one. Now, we are shifting towards specialized, less large models. Maybe not small language models, but less large language models for sure. We have found out that models, even frontier models, needs to be optimized in order to achieve the best throughput, the best computing per token, the best quality. Just making your model bigger won't fit for every kind of problem that you can face. And every architectural decisions that we faced in the very first phase has flipped. We started thinking about bigger models, from 70 billion to 500 billion and more. But now, we have sub-1 billion more models that work quite well, and less than 30 billion models that can run on commodity hardware that work quite well as well, and can be an equivalent substitution for specific tasks. And we will find out that specialization is something which is the clever point, and it is the sweet spot between frontier models and small language model. If you can specialize, if you can focus on a narrow set of tasks, you can move from large models to smaller ones. Then hosting. Hosting wasn't perceived as an issue in 2023, and it became a relevant compliance regulatory issue in 2026. And this is something that we need to consider. Then weights. Closed vendor proprietary weights models showcased that they are not suitable for optimization. They cannot be easily optimized, they cannot be easily distilled, they cannot be easily changed and transformed into other specific models. And this is a beforehand on open weights models that allow basically everyone, even startups that start from this model, to engineer new language models. Then interoperability. We started with proprietary SDKs, and then we moved. And this shift was driven by MCP and skills and all the stuff that has been released open source and then contributed into the Linux Foundation. And it is something that actually it is enabling a lot of use cases. And then data path and then unit of economics, we are not measuring more as per token. We are understanding how to move something on and optimize that on a given hardware. Which can translate not affordable OpEx into something more sustainable. It is quite funny because it is an inversion of tendency, an inversion of direction compared to the reason why we moved to the cloud. We moved to the cloud to mobilize CapEx into OpEx, and now we found out that some kind of OpExes are too expensive to be affordable for common use cases, and then somewhere we are shifting back, we are moving back these workloads into something that could be a CapEx, but could be more manageable, even because we changed the scale. The factor is that we cannot be economically efficient at scale. Maybe we will be able to do that in 1 year, 2 years, 3 years. But right now, generative AI is not efficient at scale, but it can be optimized on a lower scale. And now we are facing 3 forces that are pushing into the same direction. First one, we have the availability of models that are small models and can match on given benchmark, on public benchmark, bigger models. Then the enforcement is really close. Is 120 days away, because starting from August 2026, the AI Act will be enforced, and we will have to consider which kind of workload we are moving on AI, and if it is something that it is stated as labeled as high-risk workload, we will need to consider and to provide accountability, auditability, and we will see that it is challenging if you do not own the knowledge about the model that you're using. And first of all, we have hardware availability. Right now, this MacBook Pro, which costs, say, about a couple of Ks, or a Jetson Nano, which costs less than $250, are hardware that is suitable to run language models. And if we can optimize, if we can distill language model to be able to run on this hardware, we can just run them with no extra expense, with no extra cost. Then, the 2026 small language model ecosystem changed dramatically, and a consistent shift arrived just a few weeks ago. Then now we have sub 1 billion parameters, and we have techniques that can make these models suitable with quality that can be comparable to frontier models. And especially I want to focus on 3 techniques and to three factors. The first one, it is distillation. we will see what distillation is, and it is something that can make a model, a small model, able to perform with the same quality of a bigger one on a specific focused set of tasks. Then we have the availability of synthetic data, which are paramount if you want to, if you want to fine-tune a model. You need a data set, you need a key value pair data set that can be fed into the model, and now we can generate such kind of synthetic data using frontiers models, of course. And then we have methods that allow us to post-train our trained model. So we can align the model with something that could be our brand guideline, or something that could be our unwanted behavior, or wanted behavior, or wanted tone of voice. And we have a very proven technique, which is reinforcement learning, and a lot of derivatives from reinforcement learning. The easiest one, it is reinforcement learning with human feedback, but we have also something much more complicated than that, that allow to have a model aligned, to have a small shift in the model weights in the direction of being suitable for specific tasks. Just to be completely honest, I'm not selling you anything. This advancement, as every advancement, came with a trade-off. The trade-off is we are not using frontier models and their general purpose capabilities, and then we are focusing on task specification. So if you need a model that can basically tell you the recipe for a good carbonara, and on the other side debug your code, and on the other side be a good coach to your children, probably small language models are not the best solution. But if you can extract a single domain-specific set of tasks, then you can narrow the kind of behavior that you need. You can narrow the capabilities that you need, and then you are able to train or fine-tune or distill small language model into them. Then we have 7 different categories of models that are suitable to be used for that case. And they are open source, they are available on Llama, they are available on OpenRouter, they are available on Hugging Face. You can download them, and you can run them today. I'm not talking about the missing parts, and the missing parts are large language models which can be open source, such as Qwen 3.5, 397 billion, but they still require a huge effort on the hardware. It is an interesting field, maybe more for a solution provider, a big system integrator, or a telco operator. We have a solution, we have sovereign solution that leverages these models, but they are out of scope for this talk. What I want to show you is what we can do with models that have, say, less than 30 billion parameters, and in many cases, less than 10 billion parameters. So that can definitely run on the specific hardware. The Qwen 3 family is one of them. We have different sizes. We have bigger sizes. The Qwen 3.5, 397 billion is definitely the biggest one, or one of the biggest that is available in the market. But we also have very small variants. And these very small variants have an interesting context window size, which is 128Ks, which means that it is not too far from, say, GPT 5.3 context window. It is not too far from standard plain Sonnet 4.5 200K tokens context window. We are not dealing about 1 million. We have techniques to achieve pretty much the same result with a lower context impact. There are techniques related to, such as, say, context compaction or context summarization that can be leveraged. They are out of scope for this talk, but just to let you know that 128K context window is definitely not too small to be usable for something. Then we have Gemma 4. Gemma 4 was released a couple of weeks ago. It is one of the most interesting solutions that we have right now because it can run even on mobile devices. I'm running, actually, while we are speaking, I'm running Gemma 4 on my laptop because I've installed OpenClaw on that laptop and I'm running Gemma 4. And Gemma 4 in the E2B or E4B flavor, it is super fast. On this MacBook Pro, it can output, say, 1K tokens per second, the E4B version of Gemma 4. I can also run there, on this hardware, I can also run Gemma 31 billion, which is a model that embodies a very good set of thinking capabilities. It is quite good for a lot of narrow tasks and can be leveraged. So Gemma 4 is one of the best that we have, and it is also multimodal, which means that we can use this model for a lot of tasks that are similar to the same tasks that we used to leverage the frontier model on. Then we have a special mention for Phi4, which is a very, very small model that can be used to match specific needs, such as PAI reduction or, say, data obfuscation or data reformatting. It has been built by Microsoft, and it is super interesting because you can just run that model at scale on commodity server clusters and use that to anonymize data. Then we have DeepSeek R1. DeepSeek R1, it's able to implement reasoning and reasoning of one class or one style on commodity hardware, and it is due to the fact that with DeepSeek R1 you can choose the kind of distillation. We'll spend a few words about what distillation is in a couple of slides, but you can have different flavors, 7 billion, 8 billion models, very small models that are able to implement the same reasoning techniques. And when I say the same reasoning techniques, I refer to the fact that comparing on specific and public benchmarks, we have a result that it is close to frontier models. And in some cases, it is even better than them. Then a special mention to RCAI. RCAI, it is a startup, US-based startup, and they released a lot of set of open source models. Their approach is something that is worth mentioning because one of the founders it is known for MergeKit. And MergeKit is a tool that is able to take open weight models and merge them into a new large language model or small language model that retains some kind of capabilities from the parent models. It is interesting because it doesn't require new training of the model. So you have your Quen model trained, and you have your DeepSeek distilled model, and then you can merge their weights into a new set of models without the need to have available GPUs or to use GPUs. And they released RC Agent 7 billion, then Supernova Medius 14 billion, and Virtuoso Small 14 and 7 billions. Why so different models? Because right now we are talking about focused models. We need just one frontier model to be general purpose, but if you want to be able to address specific models, specific use cases, we need some kind of model with shaped down behavior. So we need a specific model that is able to follow instruction if our goal is to have an agent model. We need a model that is able to generate text or summarize text if our goal is on that focus. We are losing general purposeness, but we are achieving a lot of benefits in terms of costs, then compliance, and accuracy. Just to give you a glimpse about how the behavior, how the approach changed. We are not scaling parameters anymore. neither the biggest frontier models are scaling parameters anymore. We are optimizing the models. We are shrinking down to prune parameters and letting into the models all the parameters, all the weights that are really useful. So we are just removing the noise. And we have a set of techniques that embody this kind of behavior, and we have been shown that they improve the quality of any kind of language models, large, small, not so small, whatever. And the fun part is that this is the proof point. On Math 400, a 3 billion parameter llama running test time scaling outperforms 70 billion parameter dense model, 23 times smaller. Oh, sorry, 23 times smaller. You can deploy a memory efficient model locally, and it can allow you to beat a very big, not local deployable model. It is very difficult to deploy a 70 billion model on this MacBook with A6 chips and whatsoever, and it is practically impossible to deploy that on Raspberry Pi or on Jetson Nano. But you can deploy a 3 billion if on specific math tasks, the quality it is the same, basically the same, and you have a 23 per gain. And you can deploy an array of them. It is very difficult to build an array of cluster. It is very expensive, but it is pretty simple to buy, say, 100 of Jetson Nano. And then this is something that I want you to remember. It is a paper that was released at the end of last year, so it is December 2025, and they were able to fine-tune a 350 million parameter model to achieve a 77.55% pass rate on tool bench, outperforming ChatGPT chain of thought, Tool Llama, and Claude chain of thought from up to 75% point. The interesting part is that the ability to call tools, to use tools, it is something that is fundamental to build agents. So we are at the beginning of a paradox where something which is the point that generative AI field, the generative AI domain is shifting to, which is agents and capable agents, it is something for what the biggest frontier model are not the best or the most optimized solution. They showcase that fact. I want to introduce two techniques that they used and then go back to this paper, which is really a game changer. The first one is that supervised fine-tuning, it is the cheapest way to turn a generalist model into a specialist models. It embodies a teacher-student model. It doesn't embody a teacher-student model as distillation does. It just defines a set of tasks and a data set belonging to these tasks, and then fine-tune the model on that. It has a very narrow distribution. It is something that can be suitable and at a very low budget. Oh, okay. At a very low budget, such as less than $100. And it can run with quantization on RTX, really on old RTX. It can be trained on just one GPU, NVIDIA GPUs. So it is a technique that can dramatically lower the cost of training of the model, because you are not training the model. You are just fine-tuning the model on a specific task data set. Then we have distillation. With distillation, we have the capability to train, using the teacher-student approach, frontier models, say, 400 billions, 1 tera parameters, down to 1.5 billion, 32 billions, 7 billions, so very small models. And we can, without losing too much, without losing their capabilities. And here, the architecture of the model is something that it is super useful, because a lot of modern models, lot of models such as DeepSeek or Gemma, they use special techniques, which I think that was invented by Mistral, and it is called mixture of experts. And with mixture of experts, you have a formally, statically big model, say 300 or 100 billion parameters, but then you activate only a subset of this parameter when you are performing inference. And since your computing power is tied to the amount of parameters that you activate, not the amount of parameters that you have in your model, you are really running on a very small set of parameters. It is a super interesting techniques that dramatically change the shape of the landscape of the generative AI 2 years ago. And now basically every kind of models, open source model is using that, and probably even a lot of closed source models are leveraging that technique. But going back into our to our benchmark and to our paper, the basic behavior of an agent is, okay, I receive an instruction, then I have to think about what to do. So I require a language model. I need a language model that has some kind of thinking capability. Then I choose amongst my available tools to use that tool. Then I invoke the tool. The tool is basically an API. Then I collect the response, and then I iterate. I understand whether or not that response was compliant with my initial input, and then I send back the response to the user. And then rinse and repeat. So this basic workflow is the basic standard workflow of basically every agent harness out there. So being able to optimize that means that we have been able to increase the possibility, the quality of agent calling tools. But we needed a test bench in order to measure that. And in 2023, and then revised in 2024, they published a set of different tools calling benchmarks that we can use to check our models and to identify whether or not our models are working. Then back to that experiment. A single, that model was just a single epoch, supervised, fine-tuned, deliberately undercooked. So it was not overtrained. It was not trained for many, many epochs, just one epoch. And then they tried, and they found out that this was the result. The 350 million model was able to score a 77% pass rate on that test bench compared to the other model. It was an improvement, an astonishing improvement. If you compare that to ChatGPT chain of thought, because the ChatGPT version of the model that was available at the end of 2025 to be used to invoke tools, it is a 3-per improvement, and the model, it is, say, 2 orders of magnitude smaller than that one. Then one thing that a lot of people argued when this paper was published is, okay, you just hit a single lucky category. So maybe they are good for, say, invoking APIs for structural data extraction, or maybe they are good for invoking webhooks. So they repeated the test, and the test was consistent among different categories, basically all the categories of the paper. This means that something was wrong with generalist LLMs. And then a paper from Anthropic found out that LLMs tend to suffer from parameter dilution, which means that if you have really a lot of parameters, you are spending a lot of tokens and a lot of, you are using a lot of your parameters just to think, just to discuss whether or not you should call that tool. And, but in most of the cases, you don't know the kind of data that the tool is returning. So it is completely pointless to spend a lot of time into trying to figure out whether or not you should call that tool or in some way or some other. You don't have this kind of complexity. You just need to route the request to the tool. And that was an explanation about this kind of very strange phenomenon where three very small model was able to outperform really bigger models. Then, starting from this point, for these results, we should understand how to actionize them, how to use them. So what seems for me is the final question that we should answer to. And if you consider which are the layers that we have to pass through when we build an AI solution for our company, for our project, whatsoever, at the most basic layer, we have the hardware. And in this case, it can be edge hardware. So it can be Jetson Nano or workstation, such as this MacBook, or an NPU, or even NVIDIA GPU. And this is the silicon that you own. Then we have the model and runtime, and we can use shrink-down models. We can use efficient runtimes, such as VLMs, to run this model, or Llama to run these models. Then we have the need to make these models able to interoperate, to work with other systems, to invoke our system. And here is where MCP comes into the play, because MCP changed that layer. Then we have the problem to orchestrate agents, so to direct different agents. If we are focusing agents on specific tasks, we need to orchestrate them. And at the topmost layer, we have the application, your application basically in your code. Then, a few words about quantization. This is not a talk about quantization, so I'm not hosting a 2-hour lessons about that, because a lot of details of quantization are very difficult and very difficult to understand even for me. But I want you to have just a few glimpses, a few insights about what quantization is. Quantization is a method to reduce, that you implement to reduce the precision of the floating point weights that you have in your model, in order to achieve a better size of the model, or in order to achieve a better performance of the model. So you move from standard standard FP16 down to integer. So you are losing precision, or even down to 4-bit integers. And in some cases, just for, such as gamma e to b, you are going down to 2 integers. So you are really reducing the size of the model. And the question is, okay, how much quality I am letting on the table, how much quality I'm dropping, because it is a drawback. And we can see that in some cases, the loss of quality, it is definitely acceptable. Just to give you a glimpse, and something that we found out last year, say, a year and last ago, it was that quantization, it should be hardware specific. If you run at full precision, you can run basically on any kind of on a set of different hardware. But if you need to reduce, if you need to lose precision, you definitely need to run on specific hardware. And we have hardware which are such as Apple Silicon or GPUs that are optimized. And if you can see, we are losing just 8% compared to the full precision, to the not reduced model. On MLX, on Apple Silicon, we are losing just less than 10% in quality. but we have a consistent gain in throughput. In some cases, such as the NVIDIA GPUs, we got also an astonishing 741 tokens per second throughput gain. And the reason is pretty simple. The model is smaller. The model is smaller. It can run more efficiently. It can run at more speed on basically the same hardware. Just to give you a comparable example, the full precision 12.16 compared to int4 quantized, this int4 is able to run on consumer laptop or on Jetson or in Nano or on RTX 3060. It is much smaller, and it can provide a significant and improved token per second figure compared to the 14.16 baseline. This is super interesting because if you can give up a few point of percentage in terms of accuracy, say we have seen 7-8 points in accuracy, you can gain almost double the number of tokens per second and the performance of the model. I don't know if someone of you has been using OpenAI Codex. The Codex Spark model just basically uses this approach. They did not disclose a lot of details about that, but they let us understand and let us know that they are basically using a quantized version of GPT 5.3, and the Codex Spark is able to deliver more than 1K per second tokens. Okay, it is not the most accurate model, but sometimes it's not required so significant level of quality. Then in this scenario, MCP, it is something that allows these kind of specific tailored models to invoke external data. We are not deep diving into MCP. 3 points are the governance. It has been contributed into the Linux Foundation. The transport, it can either be HTTP, standard I/O. Recently, they have also implemented OAuth 2.1 in order to have MCP servers handle directly the authentication. So your language model can invoke a remote host, a remote service through MCP, and then it can challenge you back about, say, give me your credential, then following OAuth 2.1 standard, it can authenticate, then retrieve the data or perform the action. Then I would like to suggest to you to propose an architecture that can be implemented in order to leverage all the different models that we have seen. This is some kind of architecture that we have implemented with Overnet and Lydia, and it embodies a supervisor agent that is a model that has only one duty, and it is to fire sub-agents. Then through MCP, it can communicate and exchange data with specialist models, or models trained specifically on given tasks that you want to accomplish. These are a set of quite standard and common specialistic models. The librarian, something that can retrieve, that can implement and perform RAG operations on a remote vector database. Or an analyst, that is something that can run SQL statements, or it can write and run Python code. But in some cases, it is not our case with Lydia, because with Lydia, we stick on the first 3 agents. But in some cases, especially in industrial cases, you need vision. You need to classify data. You need to classify images. You can do that. You can use specialized agents for vision, for classification, maybe using Gamma 4 that we have seen to be able to implement some kind of multimodality. And going further, just really a very few words about that, putting all together. If you want to take away one disruptive statement for this session, is this one. We have been told that it's just a matter of having our servers within the EU borders is not true, is not sufficient, because a physical location, it is irrelevant when you have to comply with the law. And the law, it is related to corporate domicile. It is related to where the company that is giving you their hardware is located, where is their main headquarters. We are facing some kind of very harsh issues related to the enforcement of Cloud Act and GDPR articles, and things are getting even worse within a couple of months. And the reason why they are getting even worse is that when AI Act becomes legally binding, if your use case it is labeled as high risk, you have to provide technical data governance, technical documentation, or you have to record, provide record keeping and logging, transparency, and you also human oversight. And it is very difficult for closed source models. It is very difficult even to not have data retained when you are dealing with this service. Even in some cases, the providers are not able to assure you that data is never retained or never acquired by external people external from your organization. And in some use cases, it's not a matter of designating someone to be your data processor. It's just a matter of something that you cannot do. If you are handling healthcare data, but also if you are handling educational data, or if you are handling employment data, you cannot share this data with people external to your organization according to the AI Act. The AI Act, it is stricter than GDPR in this sense. With GDPR, you have to clarify which is your legitimate interest, and then you can provide that data. With AI Act, it's not possible. Which means that if you leverage on edge deployments, you can use these three built-in compliance properties. End-to-end lineage. You own all the life cycle of your data. Then the processing, it is, and even your IP, it is within your company boundaries, and you can implement closed loop logging, because you can log all the data going through your model, and you can see even which kind of ways are activated, and you can even understand how your model performs, because you own the complete life cycle. Just in 30 seconds, overview of some kind of use cases that we are really seeing. Fraud detection. Fraud detection is something which is critical because it handles personal account data, of financial account data of people. And we have a latency target which is really constraining. Then healthcare data, patient data. I've been working with a lot of healthcare institutions, and it is really a critical point. You cannot share your data. You cannot provide the data. You cannot contribute patient data, because patient data is something that cannot change from time to time. It's something very critical. Then, in some cases, even industrial cases, you cannot afford to have internet failure of any case. Owning the silicon and can end the scarcity argument, and it can provide you up to $250 per almost 70 teraflops of data, which means that starting from today, you can just take this picture of this chart, which is the last one, and you can focus by design on sovereign edge model deployment, and then treat every frontier public cloud deployment as an exception. Default to sovereign unless you can explain why sovereign solutions are not suitable to you. This is a conservative approach. It's something that works in practice. It's something that we have been using with Lydia, which is a legal tech domain, and with our healthcare, Schneider healthcare companies. Then the intelligence layer must operate within the boundary of your company and under your regulatory compliance. It is something that I've been seeing in the last, say, 1 year and a half, getting more and more sustained, more and more relevant for a lot of companies, for a lot of use cases. And now we have the tools to start sovereign first, to start edge first, and then understand if our use case may be in some narrow, particular subagents or aspects could be delivered, to be deferred to external frontier, public, corporate, obscure models. So start edge first, then move cloud later. Thank you very much.